Introducing Huihuo Zheng. He's a member of the data science group here at Argonne in the Leadership Computing Facility. He's a graduate of UIUC, PhD in physics, background in chemical physics, if I remember correctly. And it's been here for about 5 years at Argonne. So he'll be telling you guys about distributed training on theta. Take it away.
Okay, thank you, Taylor. So let me share my screen. Okay, are you able to share my screen, to see my screen?
Yes.
Okay, great, wonderful. So we can all, go to the GitHub repo. So today we will be talking about the distributed training. From previous lessons, I think you all have learned was the basis of machine learning, deep learning, and then even Taylor talked about preparing your data set for the training, how to kind of stream your data set from the file system to your model, right? And then we also talk about different type of deep learning models, image-based, time series-based. So, but today what we'll focus on is more on the, can say that the computing part, how to train your model faster, right? Traditionally in the machine learning community, or maybe when you do your research, with your supervisor, your supervisor give you a workstation which have about 1 or 2 GPU, and then you run your deep learning model, which might take, for example, days or weeks. Sometimes I heard that some research even take a month to train a model, right? So the goal of this distributed training is to use multiple GPU, even multiple nodes to train your model, even on the supercomputer, so that eventually you can reduce the time from weeks, days to minutes, right? So hopefully, like throughout your PhD life, if you train it with your workstation, you can publish for about like 5 papers. But then with a supercomputer with distributed training, you maybe publish about 50 papers, right? I'm kidding. But the goal to reduce this kind of time to solution does kind of help us a lot to accelerate the discovery of the training of the science, right? So that's the main goal. So and then this you can see that there are 2 parts here. One is Horovod, second is DDP. This is the 2 frameworks that will help us to parallelize our deep learning model so that they can run on the supercomputer. And I will primarily focus on Horovod, and after that, I will briefly mention about DDP. The concept is quite similar to Horovod. But DDP is more for PyTorch, whereas Horovod is more generic to like TensorFlow, PyTorch, MNXNet, a lot of other frameworks. Okay, so yeah, so I will, the schedule is that I will briefly introduce this distributed training, and then we will get into the practice, right? I set up the 3 goals of this tutorial session, and I hope that each of you can really focus on this in this next maybe 2 hours, and to achieve this goal. The first one is more of about the knowledge base or conceptually, what is the model parallelization and data parallelization to achieve this distributed training. And the second one is I want you all to be able to modify your code. Like given your code, even some people initially we develop things with Jupyter Notebook, right? And which typically run on a single GPU, and how to modify that to run on multiple GPU. So I will go through one example, which is a very simple, just an MNIX example, step by step. And I hope all of you just can follow me step by step. And after you going through all this process, I will guarantee you will think that distributed training is very simple, not too complicated, and you will be able to kind of modify any codes from your research to be able to kind of run on supercomputer, right? And then of course we want to run everything on the Theta GPU, so you will be able to know that how to run this distributed training on Theta GPU. Previously, most of you maybe just launch a Jupyter notebook and run everything on Jupyter notebook. Running the distributed training is slightly more complicated than that, but it's not too complicated. So we would learn how to run that. Okay, so just some brief introduction about the distributed training. Whenever I talk about this distributed training, I like to start with this plot. This one is from a website called OpenAI, and what they do is that they plotted the flop, the complexity of the model, and versus the time that the model were created, right? So starting from the 2012 ALEXNet, which is very simple, right? By the way, the y-axis is called the petaflop per second times day. That basically means how much computation involved in this model, in training this model. Petaflop right now, Theta is in like 10 petaflop version, and Theta GPU is 40, if I remember correctly, petaflop in the petaflop scale, right? And then the next generation, or actually frontier, will be like exaflop. Actually, even Summit, if you consider the single precision, it's already achieved the 1 exaflop performance. So, so you can see that this y-axis is basically, if you see that this 1000 means the 1000 petaflop, which is a 1 exaflop, right? 1 exaflop per second times day. So if you basically means that if you train a model with such a complexity, for example, this AlphaGo 0, with the current Summit supercomputer, right, using all the nodes, I think it's around 4,000 nodes, and each node has 6 GPU on Summit. If you use all of that and train your model, it will take 1 day to finish the training. All right, that's using the entire machine. So that AlphaGo is with such a kind of complexity. ALEXNet, we all can train this model kind of a few minutes at our using 1 GPU, right? But with as the model grow, we cannot do it with 1 GPU. And this the speed of this growth, it's doubled every 3.8 months, about like 4 months, the complexity doubled, right? So that means that people keep creating more and more complex models. And not only just training a single model, but even people also trying to find the best hyperparameter. So they do hyperparameter search. So at that case, you might train the model like concurrently with multiple instances, right? That also improve the level of complexity for training a model. So that's the reason why we need to kind of consider to train the model at large scale supercomputer. And this plot, this is a table showing you that with this distributed training, how much speed up can we get for this? This is a ResNet 50 model. You can see in 2016, when the model was just came out, it was trained with a P100 GPU. And this took about 29 hours. That means if you use one P100 GPU, it will take about 1 week, right? More than 1 week to finish. But in 2019, people use about like 2,000 V100. And then this reached to 1.2 minutes. And if you use more, of course, you can keep reducing the training time. But remember that these in supercomputer, the setup time is about 1 minute. So even if you use more, the kind of is minutes to use more GPU to train. So but anyway, this 1 minute is it's already very kind of fast, right, to train this ResNet. So that's how we can get using the supercomputer to train a model. And then the key reason that this distributed training can accelerate the computation is basically this similar to the traditional HPC simulation where you use MPI, right? Basically, right now, previously you have like one person doing a lot of tasks, but now you have multiple person, you can do the task together, right? So in the MPI or distributed training world, the key is to how to divide the work, distribute the work to the many workers. So and there are basically the two ways to distribute the works. One called model parallelization, second called data parallelization. Of course, there are hybrid mode or intermediate case like pipelining parallelization, which I will mention briefly later. The idea of model parallelization is that basically you have a neural net model which composes a lot of neurons, a lot of layers. Each layer have a lot of neurons, and there are a lot of connections among the neurons, right? So this model with this model parallelization, we basically partition this model into different workers. So here you can see that worker 1 is responsible for the first layer, and the second and the third layer is partition into 2 parts, right? And one is worker 2 is and worker 3 are responsible for this second and third layer, and then the fourth layer, the output worker 4, right? This is the idea. You partition a model, and then each worker will be responsible to compute the input and output activation, right? And then also send the output to other workers. That is the communication among this among the workers. So this is the model parallelization. It fixes the case that when you have a very large model, and then you can just divide the model and then put it into different GPU, right? But right immediately you will see that in the parallel computing, the key to achieve this speed up, linear speed up, is to balance all the works among the workers, and also to reduce the amount of communication among the workers, right? And then this model parallelization, particularly, there is a difficulty to balance the work. For simple model, we can kind of easily divide the model, the neurons. But for complicated models, it is really hard to have a load balanced way of partition a model. So that's kind of a drawback or a difficulty with respect to model parallelization. And then so in a lot of cases, the model parallelization is more in an ad hoc way, kind of manually doing things. Although there are some framework developed to help to do model parallelization. And compared to this model parallelization, the data parallelization is more is simpler. It basically each worker has a complete copy of the model, right? It just partition the data into different subset, and each worker only work on one subset. So that's the way how they distribute the work, right? Because each worker will process less data. That's why it is become faster. And you immediately see that compared with the model parallelization, data parallelization, it's more load balanced, right? It's easy to equally partition the data, right? You have 1,000 samples, you have 100 workers, then 10 samples per worker, right? Then that'll be good. And however, if you also see the data parallelization, there's also communication involved, and this communication is collective communication, where you have all the workers have to sync up. Later on, if we go into detail, you will see that they basically have to sync up the loss and the gradients before they can update the weight for the next step. Whereas in respect to this communication, the model parallelization is more kind of local. This worker only communicate with the nearby workers, right? So there is a considerable advantage regarding this communication overhead in the model parallelization. Okay, and nowadays, I also seeing a lot of people kind of start to have this hybrid mode where you have a model parallelization within a compute node. Inside a compute node, you may have several GPU. So doing the model parallelization within a node, and then doing the data parallelization across the node, right? That's for the case that your model cannot fit into single GPU, but you can fit into a single node with multiple GPU, right? So, but then today in this example, we will focus on kind of a small model, which can fit into a single GPU. We don't need to consider the model parallelization. And then the other is called pipeline parallelization. It's very similar to model parallelization. You basically partition the model in a way that it can be different worker can work in a pipeline fashion, right? So basically, like worker 0 work part of the things and then send the output to the worker 1, and then send the output to the worker 2, and then following up, right? So this is a pipeline in fashion. And of course, if you kind of know the industry a little bit, the pipeline fashion, the key kind of difficulty is to overcome any bubble, right? So basically, if the first worker doing a job take a lot of time, the second worker take less time, then second worker will have a lot of idle time, right? And while the first worker was keep busy doing a lot of things, the second worker is kind of wasting, it's sitting there idle. So right, this is called bubble. So the effort is to also reduce the bubble. It's a similar difficulty as the model parallelization to how to load balance the work among all those workers, right? So also this is a kind of more difficult than this data parallelization. If you want to kind of know a little bit more about this, because this has kind of becoming more and more popular these days, this pipeline parallelization, and then more software support is available. Okay, so yeah, so this is a kind of brief introduction about this different parallelization schemes. And then Horovod is a software framework developed by Uber to help the application developers to kind of very easily to implement this distributed training. And this plot is provided by the Horovod, basically show a schematic kind of way how this distributed data parallelization works. Basically, you partition this data, right? And then, as I mentioned, different workers There's different toolbox are different workers. Different workers have a copy of the model, and then each of them calculate the gradient with respect to the subset of the data they see, right? And then after that, they have to average the gradient, and then use the average gradient to update the model, right? That's the idea. So this is the one step, and then each step keep consuming more and more data and keep updating the model. And the model will always be the same. They will have a same starting point, and then they will use the average gradient. So the update will also be the same. So through the whole process of the training, the model will be the same. Okay, of course, the gradient they calculate locally will be different, right? Because this is based upon the different data set, different samples they see from the model. Okay, and if you want to know a little bit more about the theoretical background or implementations about this Horovod, you can check this reference. And then next, I will just kind of show how to modify the code to use Horovod. Okay, so there are basically 8 steps or 8 things you need to be careful about in order to modify a non-distributed Python code. I'll briefly go through that, and then after that we can show the example, go through a real coding example. So the first is just initialize the Horovod, right? If some of you are familiar with the MPI programming, this is basically the MPI init. Initialize the communicator, like the processor group, etc. Right? And then once we initialize, we know how many workers are working together for this training. Then we have to kind of assign the GPU to the worker, right? Like each worker manage how many GPU. Usually we only use one, right? But in principle, you can manage multiple GPU. So we need to tell the workers what are the computing resources that the worker can manage, right? And then this is regarding scaling the learning rate. I will say more as we go into the detail. And then the 4th step is to set the distributed optimizer gradient tape. This is the key step, as we mentioned that each worker calculate the gradient and loss locally, and then at the end they do an average, right? This distributed optimizer or gradient tape basically manage the average process. Then 5 is to broadcast all the model parameters before the training. As I mentioned, it's important to keep all the model the same, right? Yeah, this step is basically doing that there. And then 6, this is the same to a lot of MPI programming. If you have the sender output, you want to make sure that only one rank manage the output. Otherwise, you will corrupt the checkpoint data, right? So if you have output, even the printout statement, right? If you just want to some general information, it's only need rank 0 print out the information, it's okay, right? You don't need every rank to bring out the same information. Then 7 is the regarding the data set, how to partition the data set. So to make sure that different workers work on different part of the data set, right? So I will also mention a little bit more later on. And then later on, 8 is regarding any kind of metrics like loss or gradient accuracy, etc. Remember now the loss or accuracy each worker calculate will be based upon the local data set they see, right? But in order to get a and the overview, the overall view of the overall accuracy or loss, we have to do average across all the workers, right? So yeah, this is basically the 8 steps, and I will show that basically next time if you have a new code, you just check. This is basically a checklist. You just go through that one by one, and then it will be good enough. And then this, I show here also the code example for like TensorFlow, PyTorch, Keras, and that you can directly copy to your code later on as you are trying to instrument your code with Horovod, right? I also just briefly go through that. For example, the first one, initialize Horovod. It's very simple, right? You just import the Horovod modular. Here, TensorFlow, you just import Horovod.TensorFlow. If it is PyTorch, Horovod.PyTorch. Very simple, right? And then Horovod init, initialize the communication. Once it is initialized, then each worker will get an ID. So this ID can be retrieved by using this Horovod rank, right? Horovod rank, then you can get a rank ID, right? Once you have the rank ID, this is the ID for each worker, then you know how to assign work to that worker, right? So this is crucial for all the MPI programming. And size is just tell you how many workers in total, right? And Horovod also, there's another one called Horovod local rank. This local rank is the rank ID with respect to that node, right? So suppose you're using like 16 nodes, each node has 8 GPU, then this local rank will run through like 0 to 7, right? 0 to 7. This is important, especially because the GPU on each node is specified by like 0 to 7, right? So when we ping this GPU to the worker, we have to use this. This is essentially what I'm talking about now here, is that this is the way how to assign GPU to each rank, right? I basically set visible device. This is pretty similar to the CUDA visible devices, and then you provide the list of the GPU ID, right? So here we just select local rank. So basically, each rank will get 1 GPU. Each worker will get 1 GPU. By the way, sometimes I use rank. Rank is an MPI language. So rank and worker or processors will be the same. So if I say these 3 words, it will mean the same thing. Okay, just to clarify this. And then scale the learning rate with respect to the number of workers. So when in your model, you usually define this optimizer, and this is a learning rate, right? And in this distributed training, data parallel training, we have to scale the learning rate with respect to the number of workers. I can give you a so-called hand-waving argument why we have to scale linearly, right? So this learning rate is basically a step size in your optimization. And now, because we are using multiple workers, so we are consuming more data at each step, right? If we keep the mini batch size the same, that means that each worker will consume the same amount of data. We just scale out the number of workers, then at one step, we will consume more data, right? More sample. And that means that we have to jump a larger step, right? Larger step. So that's why this the learning rate should be scaled linearly, right? There are kind of a little bit more rigorous argument why we should scale this linearly. If you're interested, you can check the paper. Then this is the way how to write this gradient tape. Yes, and then later on, we have to broadcast this model and the optimization, the initial state to other rank. And checkpoint only rank 0 to the checkpoint, right? Just you put the if statement here. If the rank ID is equal to 0, then save the checkpoint. Otherwise, do nothing. And loading the data according to the rank ID. This is to partition the entire data set into different subset, and then each worker only work on one of the subset, right? So there are potentially two ways. First way is you just manually partition, right? So you just kind of let worker 0 only work on this part, worker 1 only work on the other part. And I will show in the example, I will show this is the way I will do, right? But you can also do another thing. You just kind of relies upon the random number, random process, and because in each time when you read the data, read the samples from the data set, you read them randomly, right? And so if you just don't do anything, but now you have multiple workers. Basically, one worker have to use a 100 step, then 10 workers can only use a 10 step, are able to basically cover the entire data set, right? Assuming that different workers will grab different samples. The overlap between the different batches are small across the workers, right? With that assumption, we can basically still do the same thing. Each worker grab randomly from the entire data set, but then we just at each epoch, we just reduce the total number of total number of steps, right? Because we have more worker grab those samples now, right? But of course, in reality, because each worker doing randomly, there might be the case that they have some overlap. So different workers might see the same data, might process the same subset of the data, right? So there's still some possibility, but because of the random process, the possibility is small. So yeah, you can also rely on that. I can show you later on how to do that if you just, yeah. And then later on how to do average the matches across the workers. Just use the Horovod or reduce function and then put a variable name. Okay, so this is the steps. So now let's just get our hand dirty to manually really change a code. And the code sure is I want to show you the code in the Jupyter notebook first. So I think if you go to let me see how many people we have. 41 people here. Probably we can all grab a single GPU now. So if you all log into Theta GPU, go to this page. I'm sure you're all familiar with this, but if you want me to kind of slow down the demonstration, just let me know. Okay, so log to GPU. I already logged in, but I want to show you. So I want to stop the start and then start. I want to grab a single GPU node. AITP and then single GPU. This step, yeah, it's okay. If you just want to see me run through the Jupyter notebook, that's okay. You don't need to kind of follow me step by step. But after that, when I modify the code, I suggest you to follow me step by step. Okay, I'll just set up this first. Hopefully I will get one single GPU node soon. And then if you already log into theta or theta GPU. And so this is I have you can do the git column. So this is the folder, the GitHub repo, and the example, all the example I have for today is in this distributed training folder. And the example that I want to use is this one, original. I will show you. Here I have TensorFlow, PyTorch, and Kairos. These three frameworks for this MNext example. In the demonstration, I just want to show like the TensorFlow example. And then later on, after this training, if you are interested, you can modify the other like Kairos code or the PyTorch code, right? So see this TensorFlow to MNext original is the one without the Horovod implementation. Same thing for PyTorch. PyTorch MNext original is the one without Horovod, right? Kairos also. So, but the other one, like just TensorFlow to MNext without anything, then this is the Horovod version. I can briefly show. Okay, so you can see there's Horovod implemented here, right? So this is you can say the answer, right? So what I will do later on, I will make a copy of this one and then copy to HZ, right? HZ is my name, right? You can also make a copy to a different name, and then you just modify this one. And the goal is to make this one able to run with Horovod later on, right? Okay, so let me check, go back. Okay, I think I already got the single GPU. No, so I want to see the code in the Jupyter Notebook format, which you might be kind of more familiar. So the code that we will be working on is the TensorFlow MNext original. I have this Python notebook version, Jupyter Notebook version, and then the TensorFlow MNext origin.py is basically the same thing. I just copy everything to a Python notebook, correct? To a Python code. So, you know, I just go through this step by step. If you're not, okay, let me see. Okay, complaining. Let me see whether I'm.
You're going to want to change the kernel back in the notebook.
Okay. Okay, I see. Change kernel. So I will probably use this Conda 2021 version. So just wait a few. Right. So this code is very simple. I just show you again, just kind of remind you the whole, you know, the deep learning code. It has, we just load the modular and then parameter, number equal, learning rate, data set, right? And then the model training. I will go through this in a few seconds. Just wait for this. Yeah, loading this TensorFlow modular for first time will take some. Yeah, well, we were waiting for this. Okay, done. Okay, good. So I'll just run through these cells. Parameter data set. This data set is just load this using the Kairos data set loading, and then we can check the training number of training samples is 60,000. The test or validation set is 10,000, right? And then it's initially this format is this, each image is 28 by 28 single channel, right? When we use the fit into the model, we have to kind of create another axis like 28 times 1, right? The third dimension. This is the reason that we create a new axis, and this is what Taylor talked about. It basically create a data pipeline using the TF data library, right? We create initially, this is just a NumPy array, and then we create it into create a pipelining using this tensor slice method, and so that we can stream this data set, right? And again, we can check the number of sample. Yeah, you see it. Yeah, I think I run this not the first time, so the data set it's already downloaded. It's just loaded into the memory. But if you run this first time, you will see that it will try to download from the website, and that's test something, right? So I grab the first batch, and then I take out the first 8 images, and then I plot the images, and then also the label, right? The label is basically the ground truth. So you can see here the result that I run, right? So you can see basically, okay, everyone is correct, right? And now we define the model. The model, I use the Keras different layers, just a few convolutional layers and some dense layers. I think this is exactly AlexNet, if I remember correctly. And define the loss optimizer. Optimizer already have the learning rate, which is 0.001 checkpoint. And so this is the model. And I want to kind of check how accurate this model is, right? So this is before training. So let's run this. I basically plot the image again and also plot the prediction from the model, right? This is the probability prediction. And the bracket, the number inside the bracket is the ground truth, the label provided from the data set, right? So you can see, okay, it's not right, right? I don't know whether this times a lot of 7, but again, it's randomly generated. So maybe we run again. So okay, so change still a lot of 7, but fewer. Okay, it may be due to the different initialization, but again, it's just the thing is before the training, the prediction is not correct. And then we train the model, we define the training step, right? Each step just calculate the probability, calculate the loss, accuracy, and then apply the gradient. Once we have loss and gradient, we can go back and then update these all the weights, right? And then in the validation, just calculate the total loss and accuracy with respect to the validation data set, right? This is just a define 2 function. Okay, and then this calculating the total number of training step and test step. And then this is the training loop, right? So each time for each epoch, and then each batch, I take the batch, I calculate the loss and the accuracy from the training step function, right? And then I just add up all those loss from each step and get a loss and accuracy for the entire data set, right? So this is for the training data set accuracy, and then this is for the testing. And then I also kind of keep track of the accuracy and loss for each epoch, right? And let's run through this. This is, yeah, so you can see at each epoch, I probably didn't remove the checkpoint. So this accuracy is quite high even at the first. Oh, there's some little bit error here, maybe some times per epoch. Okay, here. Let me run it again. But before that, I want to remove my checkpoint. So, okay, somehow I still get a very good result. Okay.
Now it's probably using the same model that you just had before, right? It probably loaded the checkpoint the first time and then.
Right. I have to reload. Yeah. Good point. Yeah. Let me do it again. I have some issue with my. Okay, so let me execute this one. So it will start with the. Okay. Still very high.
Maybe restart the notebook.
Start the notebook.
I mean, yeah, it might, give it a hard refresh.
Yeah. Okay, this is another kind of.
Yeah, not that important anyway.
Yeah, we can go back later. Yeah, but if you, I think, maybe we can restart the notebook. If you try, you will see probably you'll get a lower accuracy here, right? In total it take about like 12 seconds. Then you can, here I just plug all this loss in accuracy, because maybe it's reading the checkpoint or the model is already in a good stage. Yeah. So this is, okay. Yeah, I think we spent a lot of time in just go through this model, I just, so that we can kind of get an understanding, a deep learning code. There are various parts, right? We go back, we just have the data set part. In distributed training, we have to manually partition the data set, right? That's what we already said previously. And then in the model part, we don't need to change too much, but the optimizer, we have to wrap it into a distributed optimizer so that it can calculate the loss, but also average across the worker, right? And the checkpoint, we have to kind of make sure that only the rank 0 do the checkpoint, right? So, and then we have the training loop, right? So data set, model, training loop, right? These are the three parts. Usually I look at this a training code, right? I will look for these three parts. Okay, now let's go to the code. Okay, if you are able to log in to Theta GPU with a terminal, then we can start to, let me move this to work on this. But if you are in maybe a Windows machine and then you don't have a good way to SSH to Theta GPU, the way you can do it is that you log into a Jupyter notebook and then you can do, let me go back to here. You can create a terminal here also. Right, you can also create a terminal here and then go to that, right? Or if you are comfortable, you can also go to the directory, just manually add it with the text editor. For example, if you can add it directly here, right, like this. So I will show the example on the terminal. Okay. So yeah, sorry for the noise. Okay, so the first step, we will just copy. If you haven't done so, copy this file, and with okay, and then what I'm going to do, I'll just go step by step. Later on, if you are doing your own code, you can also do this, right? Just put these two windows side by side, and then we know the step, and we can just follow this step. Okay. If you want me to slow down the demonstration, also let me know, okay? If it is too fast. So hopefully you all get to this step. You open up this GitHub repo, this README page, and also open up this code, right? And then we can just modify this on the fly. Okay, the first step is that we have to import this modular and then initialize Horovod, right? This should be in the very beginning. So I will comment the first step here and then import. Okay, somehow I'm showing the tensor carrots. Okay, I'm doing this TensorFlow, right? Should be here. And then initialize. Okay, and I usually do a sanity check about this ID. And so this is the first trivial step. The second step is to assign GPU to each rank. By the way, the code I'm working on is exactly a copy of this Python notebook, but I add something basically for the input, right? We can command line input using the argument parser. Okay, let's find out where we can add the pin the GPU. So here we have the GPU list, right? And so what we want to do here is to pin this. We have the list of the GPU. We can directly copy this code here. Okay, right. Okay, let me mark here. This is the second step. The third step is to scale the learning rate. So learning rate is specified in the optimizer. Okay, actually, this is something I left behind previously. So initially it will be like this, and then this will be the case, right? Third step. And then the fourth step is wrap this gradient tape. Okay, I think this is all again left behind from previously. So this is a non-parallel version is like this, and tape is defined here, right? We have the tape, and so we just
there's a request to see step 2 again.
Step 2. Okay. Here. Kyle, any question
for this?
Not yet.
Okay. Okay, then step 3 is to wrap this tape, right? Using the, oh, actually step 3 is gradient. Let me double check. I already skill learning anyway. Okay, step 3, this should be the step 4. I just copy this code. Okay. Yeah, and then this step 5 is to broadcast the model from rank 0, right? For TensorFlow, this should be done, after the first step, because the reason is here. I put here, right? The broadcast should be done after the first gradient step to ensure optimizer initialization. So this is defined to be the training step. So the place that we finish the first step should be here. So we have the training loop here. And then the first step, this is a batch loop. So the first step should be like this, right? If equal index equal to 0 and batch also equal to 0. And then we do the broadcast. We can copy this. Oh, right. But sometimes we have to change because the model name I was using list. Okay, this is step 5. Right, there's a broadcast the model and also the optimizer state, so that throughout the whole training, the model on different workers will be the same. Then checkpoint on the root rank only. Okay, let's find out the place where we do the checkpoint. So here we have the save the checkpoint. So what I will do is to add a condition here. Only Horovod rank equal to 0 to the checkpoint, right? So that we won't corrupt the directory, the file, the checkpoint file. We probably have other place, if I remember place. Okay, another place here. This is saving the final model again. Okay, and also the output, right? We don't right now. We have multiple. We'll be using multiple workers to run this code, so we don't want a lot of kind of output from all the workers. So again, this print statement, I will use this. Okay. We have also another print statement. Oh, this is okay. This is save the matrix on each. So I think we also have to do this because this is also saving the output. We only want rank 0 to do that. This print statement we also want. Okay, this is the step 6. Let me mark 6. Okay. Now 7. Loading data according to rank ID means that different worker will have a different data set to work on, right? So let's go back to the data set session. This is the data set session, right? So we can do, the way we can do it, we can do two things. First is that from here we have the load the data into array, right, into a NumPy array, this training and the test. We can, and then this data set object create this pipeline from this NumPy array. So we just slice this NumPy array, right? So what we do is that the way to slice a NumPy array is like this, right? Basically, every other, if I have 8 workers, for example, this will pick up the sample with spacing 8, right? Pick up 0, 8, 16, and then rank 1 will pick up 1, 9, right? That's the way we kind of partition. And of course, you can make it contiguous, right? That the worker 0 work on the first contiguous chunk, worker 1, the second contiguous chunk, right? In this case, these two will be kind of similar to each other, not too much difference, because at the end, all the workers together see the entire data set, right? But in the performance space, when you are slicing this, right now, we're actually, this step, we load everything into memory, right? And then we create a pipelining. But if your data set is too large, that you cannot read the entire data set into the memory, then you have to kind of read them from the file system each time, right? So your streaming will be from your file system. So say for example, if you create a HTML5 object data set, then you can slice the data set, HTML5 data set, the same way as you are slicing a NumPy array. In that case, your slicing, it's better to do it contiguously, right? This is just a side note. So because a contiguous chunk have a better I/O performance, doing this, like pick up, not contiguously, will have a poor I/O performance. So if you're kind of loading data from your file, remember to kind of slice, partition this in a contiguous chunk. Okay. Okay, so right now, because the data set is small, we do everything here. So it's easy. We just do in this way. Same thing is for the label, right? Again, for the test, we also have to pick up the sample. Okay. Yeah, so we have the data set being partitioned. Yeah, and then I might want to kind of do the shuffling buffer smaller, because in total we only have 60,000, right? And now if we use multiple workers, each worker will get below 10,000. So we don't need that larger shuffling buffer. Okay, so we have all those 7 steps. The last step is to average the matches across the worker. And this is particularly when we want to print out the loss and the accuracy. Right here, if we are in this, initially it's just 1 worker, so we don't need to do average, and we just print out right away, right? But if we want to do the average, yeah, I won't do the average every step. I will just do average at the end of each epoch, right? So just remember this printout will still be, here it's inside of the step loop, right? Different step, and then it print out the loss per 100 step, and it is not too kind of efficient if I do this average each inside of a step loop, right? I will just do average per epoch. So just remember that this loss value will still be a local loss, not the average loss. Okay, so total training loss equal to or reduce. So this is the local value, and we want to do average. Average is true. Average is true means that you divide it by the number of worker. If it is false, means you just add up all the training loss, right? Because the way in the deep learning, when they define this loss, is divide the total number of sample, right? So that's why when we average, we also need to divide the total number of worker. If you do the math correctly. Okay, and then validation loss. Oh, sorry, should be training accuracy. Okay. So we have the total training now, and then after calculating the loss, test loss or test accuracy, we also, sorry to kind of confuse you with test and accuracy. I'll define this to be validation accuracy equal to we are almost done. I'll modify the code, and then we can test whether it runs properly or not. Okay, and then when we do this, we should also modify this. Modify this first. This is the printout after, at the end of each epoch, it print out the total training loss. Accuracy. Okay, so this I appended to a kind of a list, right? But I want to change because this one is defined as a TensorFlow tensor. I have to change it into a NumPy array, a number, right? So I can now just put this tensor into this array. I think that's it. Okay, so we can do now. Then the next step, we have the code. Okay, that's before closing. I'll just go through every step. The first step, again, is initialize the Horovod, right? The second step is to pin the GPU, right? And this variable Horovod local rank is important. The third step is to scale the learning rate. The fourth step is to define the distributed tape. The fifth is to broadcast. Oh, sorry. It's good that we double check. This should be in the training loop. So after the first training step, right, we broadcast. Usually in Kairos, in Kairos or in PyTorch, you broadcast the model and the optimizer before the first step. But TensorFlow, somehow we have to broadcast after the first step, after it was initialized, and we broadcast. This is particularly to this TensorFlow. It's good that we check. We previously placed it to the validation loop instead of the training loop. Okay, and then 5, 6, the 7th, we also do the manually partition the data set, right? We slice the array so that each worker will only work on a subset of the data set. And then we also average the matches so that the loss we plot out is not the loss from a local worker, from a single worker, but actually the average. There's a typo here. Okay, we can update them. So now I think next step is to run this. Yeah, if some of you we can grab a node interactively, or we can do the submission. So just submit a job. I create this submission here. We can go. This is the way to submit a job, TensorFlow MNIX, right? So I here do basically a scaling test. I load over this environment. This is a, set up the Python environment and then run this. When we run, okay, this is just to remove the checkpoint so that every time it will start from the beginning. And we just run with MPI, and we specify different MPI processors, different number of MPI processors, and run this job and put the output, right? And the last one, command them, is the profiling, which I will mention later on. But this, if you do this QSub, it will run everything, right? So this one is 100% correct because I already tested, all right? But the one we just modify, we might need to go through some debug process. So yeah, this one is already correct. And if you want to check the result, I would suggest maybe you can do the QSub. Just do QSub submission, and then this one, the TensorFlow MNIX. Okay, from the login now, I will submit this one. Okay, then we can check. You can do it QStay your username, right? It is running. It is already running, right? It is starting its job. Then you can later on can check all the results. So as I remember, I think I want to modify one more thing here. But anyway, the code here it's correct, so we will get the result later. But the code we just modify. I think there's one more thing I want to change. Is that I want to make this output depend on different number of nodes, right? This matrix I want to kind of later on, because I want to do a scaling experiment, like running with different number of workers. I want to do like this. How size. So that different number of workers will output. I mean, if I run with one worker, we'll have matches 1.dat. Okay. So since I already have an interactive node open up here, so I can just run job interactively. If you want to run job interactively, you can also do qsub. There is a command here. So, but still remember, we have set up the 15 minutes limit for the wall time. So you can only run 15, but 15 is long enough. So after logging to this theta or theta GPU login node, after theta GPU login node, you can do this. Then you will get, I already have that, so I don't need to run, but you can do this. Then you will open up an interactive section here, like this. This I already set up the environment. After you get the interactive node, get the node allocated, and you can run this command to set up this environment. Okay, to set up this environment. Let me do after you set up the environment, you will see that this is a conduct base, right? This is a virtual environment. That means that we have this environment set up. So then you can now we can run, right? First, I want to run with single processor, single worker, just to check whether there's some result. And if you were not able to follow me to get your own file like this, you can run the file I provided here, right? For example, yeah, I will just run the file I just modified. So let's wait. Yeah, one worker, and they print out I'm worker 0 of 1, right? Because only one. Let's see whether we hit any error or not. Oh, yes. So there is a typo here. Model.mlist is not defined. Okay, I have to find out what the parameter defined. Or mlist model. Mlist model. So this is the challenging when kind of doing this hands-on tutorial step by step. So okay, hopefully it will run. Another typo. Oh, I haven't defined the time per equal here. Yeah, okay, so it runs, right? So you can see now this is the local. I haven't averaged, right? I averaged which is at the end of each epoch. So epoch 0, we're getting the accuracy 0.89, and then gradually increase the accuracy. And I run for 16 epoch, right? And the total time is about 27 seconds. So this worked. That's great. That increase the number of workers to 2. See whether we can get speed up, right? A product that's 2 workers. Okay, 23 seconds, right? We get some speed up, but not as a twice speed up. We later on I will say why this is, we didn't get a 2x speed up, right? It's because this model is too small, and the initialization process take a long time, become a dominant. We will see later on in the profiling result. But we can finish up this 4 worker run. Right, 4 worker 13 seconds, right? We get a little bit speed up, better speed up compared to the 2 worker case. And then finally, the 8 worker case. Okay, this is 15 seconds. Actually, this 8 worker is even slower than the 4 worker. That means that it doesn't scale from 4 to 8, right? So running with 8 GPU is not faster with this because of the initialization, right? So this okay, so we can check, there's also a way to check what's the problem about the scaling, why we didn't get good scaling, right? So here I put if you see the left panel here, I put all the timings that I run previously for the 16 epoch, the total time, right? The first in 1 GPU take about 28, and then 8 GPU 14. Right? We get some speed up from the 1 GPU, but not too much. And actually, the problem is that it's because the first epoch, it took a lot of time. The first epoch is because of the initialization process involved. If you can see here, yeah, I actually brought out all the timings for epoch. Like in this 8 GPU case, you can see that first epoch take 11 seconds, and the second epoch is that take less than 1 second, right? And then less than 1 second. So there is an initialization process going on in the first epoch, and this initialization is kind of almost the same whenever you are using 1, 2, or 4, 8 GPU, right? And because our model is too small, we didn't use that many epoch to finish all the training, right? So this initialization process become a dominant time. And if you later on, if you are doing this Horovod for your own code with a bigger model, then the speed up will be much better. Ideally, I think you should be able to get 2x or 8x speed up when you're from 1 to 8, close to 8, AX speed up, right? And then there's also profiling. We can profile the code, and there is a tool called Tensor Horovod timeline. And the way to get the timeline, it's very simple, just to define the environment parameter called Horovod timeline and specify the output. There's also MPI profiling, that you can see what are the MPI communications, the function code involved in this distributed training, which I won't go into the detail later on. If you're interested, you can check. But if you specify this Horovod timeline with this JSON file output, and then run this example, then you'll get this JSON output, and then you can download this output to your local machine and open up this file with Chrome browser. So here I already opened it up. Then the way to do it is just this is the address Chrome / trace, and then you load the file. Load the file and just specify this timeline.json. I already loaded, so I won't load it again. And once you load it, you can find a timeline. Timeline means that, and this x-axis is the time, and a different block are the different operations happens in this training. And you can see actually the whole thing is initialization. You can in the LICO is a communication library for GPU to GPU communication. So it uses a lot of initialization time. And then later on we run 16 epoch, right? And this is the time per epoch. You can see this periodic happening. If you zoom in, you can also see more detail, right? More details, which I want to go into detail now. But this is a good thing for us to kind of know how much time it takes in communication, how much time it takes in computation. Later on, if you are kind of interested more on the performance, on the scaling efficiency of the code. Okay, so yeah, I think that's the Horovod part. Yeah, I don't know whether you're able to follow all this example and then run this. If you are not able to generate a code, you can just run this and run the code that I provide here, right? If you are familiar with other framework like Keras, PyTorch, then you can spend some time to modify this code and then compare with the result the code I generated. I mean the code I modified. Yeah, and then finally I'll just briefly mention about the DDP. And then this is the code here again. The same MNIX example, but with Python, PyTorch framework, right? It's quite simple. You can just go through into the details. And I just pointed out the things that we need to modify. First, this PyTorch, this DDP is building in the PyTorch. So it works only for PyTorch. And it's better than the Horovod for PyTorch. So if you are in a PyTorch, if you're using PyTorch for your model, then I would suggest use DDP instead of Horovod. If you use TensorFlow, then use Horovod, right? Because the Horovod integration to the PyTorch package is not as good as this DDP. And then for this DDP, a lot of things are quite similar to the Horovod, except that it needs some initialization. The initialization part is a little bit complicated, but not too much complicated. It uses the MPI for the MPI communications, and then you also need to set up a bunch of environments for the PyTorch package, and you can see the detail here, which I won't go through it item by item. And then regarding using this DDP is to wrap the is just to use the DDP to wrap the model. You know, in compared to the Horovod, we wrap the optimizer or the gradient tape, right? Because the optimizer and the gradient tape are doing those or reduce, doing those averaging. And with DDP, you just can wrap the entire model, right? And then everything else are quite similar. We can go to this code briefly to see, you know, this is the setup things I mentioned, and this is also an initialization, another part of initialization. And then other things are similar. In the data set, we also do manual, do partition. PyTorch, they have a data loader, distributed data sampler and data loader that can do this automatically for us. We don't need to manually slice, do the slicing. Right? So this is the same with Horovod. You also do this. And then wrap this model and scale the learning rate. The learning rate scale for the number of worker, right? Scale the learning rate. And then checkpoint, print out stuff also just like rank 0. I think everything else is similar except the wrapping part. One is wrapping the optimizer, one is wrapping the model as a whole, right? And average, we also need to do the average of the matches, and yeah, everything else is the same. Okay, you can check this in detail. So yeah, I think that's all the things that I want to talk about. I'm happy to take any question, or if you have any issue you got when you are running those examples.
Thank you, Huihuo. People have been putting their questions and having them answered in Slack. I think things are going well. Check the queues real quick. I see some running. I don't know if anybody has any questions. Otherwise, the questions in the, submitting your questions in Slack is perfectly fine, and we'll keep answering them there. Our reservation on Theta GPU goes until 5, at which point that will be released. So you can keep working with the examples up until 5 o'clock. Use the reservation queue. I think it's called training. So when you submit with QSub for the full node queue, like if you want to do multi-GPU training, use -Q training when you're submitting up until 5. After 5, you can just use full node.